because we were talking, or now we can actually maybe talk a little bit about the spectrum itself, going through the spectrum. So technically there are things on both sides, right? We can start with the visible, and then we can or do you want to start with one side and go to the other? Because I was okay. So like, for example, the best way and to start with this whole thing, right, is what was I gonna say? The fundamental notion of the electromagnetic spectrum is that light and energy, or the energy that the light carries, is related to this color that we perceive. That is that fundament. So the type of light, the type of placement in the electromagnetic spectrum, when we say infrared, when we say X-ray, when we say microwave, whatever, completely and utterly depends on the energy of that given light. And the energy of that given light depends solely on the frequency of that light, or you can also say on the wavelength of that light, right?
Oh, wait, 1 second. I just got to explain something real quick.
Go for it.
This actually relates to the speed of light. Because hold on. Let's think about something real quick. If the speed at which the wave is moving is constant, right? Then the only thing that can really add energy is the wavelength. You know what I mean? So imagine you have like this interval of, let's say, 1 meter, and you're going up and down, you're waving like slowly, right? And then you have another interval, same length, right? But the wave is moving at the same speed, but it has to go up and down more times in the same interval, right? Intuitively, you can say that the one with the shorter wavelength has more energy, right? Because it has to, like, this is just an intuitive, like, hand wavy explanation. But it's like the wave has to travel more, like, up and down, up, like, very, very, very quickly. And it has to make it from one side of the interval to the other side in the same amount of time as the slow moving one, the one that's just going up, down, up. So intuitively, when you shorten the wavelength, there's more and more energy. And so when you actually study the visual spectrum, you see that the highest wavelength color, lowest energy is red. And then as you move up the wavelength, you go all the way through the rainbow, all the way to purple. And so the reason we call it, violet, sorry.
It's called ultraviolet, man. There's a reason it's violet, You
want me to call it Margaret? I don't know. Indigo, I don't know.
Indigo, you have to.
So infra means like under, right? Infrared, under red. And then ultraviolet, above violet, okay? And then in the ultraviolet range, correct me if I'm wrong, but it goes X-ray, then gamma rays.
Yeah.
Gamma rays being the highest energy photon type.
So this is going back into that gamma radiation talk, like quick snippet that I was talking about here, with the high energy photons are released. So in radioactive decay, when these electrons are jumping, down onto a resting state, because I mean, when any element is decaying, it releases a bunch of particles, alpha particles, beta particles, gamma particles. And these gamma particles are these photons, these high energy photons, right? And that's on the spectrum. So anything over, and again, these are all very discrete levels. And I believe a lot of it is just, obviously, like, it has been studied and whatnot, but a lot of it is simply our understanding of the spectrum. Like, I'm pretty sure there can very much be higher than gamma, right? Like, what's...
Actually, so this actually ties into the Planck length, because...
But gamma doesn't limit at Planck. There's no way, does it?
Well, the shortest / highest energy photon ever possible would be the Planck length.
Exactly, when the wavelength is equal to the Planck length. Exactly.
And I think gamma ray just, like, goes all the way
I
up,
guess, I
you
guess,
know?
I guess gamma is just what we call all the way. And we were talking
Yeah.
about infrared and talking about on the other side of infrared, so sub-red, we have radio waves. So these are
Mm.
the most popular type of waves that we use, and all our cell towers, everything, FM radio, for example, is all based off of radio waves, right? Oh, wait, we didn't get into microwaves. Microwaves is after ultraviolet, before X-rays. So that's microwaves. And interestingly enough, microwaves have microwaves. Not a lot of people actually think about that. Like, when you say I have a microwave in my kitchen, like that microwave, the fact that it produces these electromagnetic waves, not a lot of people know that. And these microwaves are, interestingly enough, because they're higher energy than visible light. So we can't again see them, right? Because it's higher energy. Anything after the violet we can't see. So the microwaves basically simply excite the water and heat up the water in your food, hence heating it up. Anyways, I mean that's another topic. But talking about the microwave in a microwave is an interesting topic on
and
the higher section of light.
something interesting about microwaves
Yeah.
is that the reason why that sometimes like one spot is cold and another spot on your plate is warm is because when you turn on your microwave, it creates this interference pattern, this like three-dimensional interference pattern of like constructive waves and destructive waves inside your microwave. And the way your microwave is actually built, it's made to like annihilate the field outside, like the way the material, the box is actually built, it kind of conceals the whole like deadly warming up part to the inside of the microwave. And then basically, if like one spot on your plate is like not crossing like a constructive area of this microwave field, I guess you can say, then it just, it never gets the effect.
That's also why I guess
the heating up.
the food rotates in a microwave, right? So it can hopefully get all the different parts in case any one particular was not accounted for. So that's actually nice. And also because you brought up the thing that, it's dangerous outside of the box. So, Jesus, sorry. So all of these higher energy light, ultraviolet included, even ultraviolet, but obviously the higher the energy, the worse, are all carcinogens, almost you can maybe call them, because they all are cancerous forms of light. Reason being, they are shorter, again, in wavelength. They are shorter and therefore are able to penetrate our skin. And because of that, they are able to mess with the DNA and mess with the tissues, causing small mutations here and there, which then causes along the road cancer, right? So usually that's why you never ever put a pregnant lady through an X-ray, because that could cause cancer to the kid, for example, because obviously lack of whatever. Don't want to get into that part, but I'm just trying to give you the reasoning behind, higher energy. The reason it's also, bad is because it's bad for our bodies, literally because it can penetrate through it. And usually it's what we, relate to cancerous radiation. Gamma radiation is primarily cancer radiation. So when we ever talk about, again, I keep going back to the bombings example. I don't know what's in my head, but anyway, going back to the bombings example, like even if you weren't in the blast radius, there can be a huge radioactive radius, and that is actually even more dangerous, because then your kids will all have some form of mutation. And this has actually been seen in Japanese cities and stuff like that. This conversation got really dark, I'm sorry, but
right.
but I just wanted to bring up how the relationship between high energy electromagnetic waves and us.